So welcome to the Picture Language Seminar. You can see we have a very interesting group of upcoming talks. Feng Xu, Jan Lacan, Svetlana Jitmirskaya, Francis Brown, Zhenwen Ha. And today we're really happy to have Xun Gao, who's a postdoctoral fellow at Harvard University. He's in the group of myself and also Misha Lukin. And he's going to tell us about a very interesting topic, which is not yet fully resolved, understanding the linear cross-entropy benchmark in terms of a statistical physics model. So Xun, we're very happy to hear your talk. Please share your screen.
Thanks, Arthur, for the introduction. In this talk, I'm going to talk about our recent work understanding linear cross-entropy benchmark through a statistical physics model. This work is done in collaboration with Marcin, Qingning, Songwan, Misha, and Boaz. Here is the outline of the talk.
You should tell their full names because it's very hard to understand so quickly.
I don't know how to pronounce some person's full name, so maybe just skip it. Okay, here is the outline of this talk. First, I will give a very brief introduction to quantum advantage based on linear cross-entropy benchmark. And then I will give an overview of our results, including a new spoofing algorithm for Xcb test and their implications. Third, I will give an approach to understand our spoofing algorithm by mapping Xcb to a diffusion-reaction model. If time permitted, we can talk in more detail about this mapping. And then conclusion and outlook. So first, quantum advantage based on linear cross-entropy benchmark. So quantum advantage, also known as quantum supremacy, is a very hot topic recently. There are two experiments claimed they achieve quantum advantage. One is Google's Sigma chip, which is based on superconductor qubit. Another is Ustc's Jiuzhang, which is based on photonics. So the meaning of quantum advantage is that an experimental demonstration of the computational power of a quantum device such that it is far beyond that of any existing classical devices. So the achieving quantum supremacy advantage is very important since it constitutes a milestone of quantum technology, which represents the human's ability of high precision control of complex quantum system. And it also challenges the so-called extended Church-Turing thesis, which is the foundation of computational complexity theory, which states that the concept of computational efficiency is independent of physical realization of the computers. So if we achieve quantum advantage, which means computers based on quantum physics is more powerful than that based on classical physics. So the current quantum advantage experiment is based on sampling-based protocols. The sampling-based protocol is suitable for near-term devices in contrast to implementing quantum algorithms like Shor's algorithm because it only requires like 50 to hundreds of noisy qubits. And although it is much simpler than running quantum algorithm, it also has complexity theoretic support. So following is the following is a demonstration of how sampling-based protocol works. Suppose we have a quantum device, which could be Google's Sigma chip, which is a type of random unitary circuit on a 2D array. And then we mirror this device in computational basis. We will get a bit string X, and then we repeat the measurements many times. We will get many bit strings, which is sampled from the probability distribution QX defined by this quantum device. And then the statistics of these bit strings is believed hard to simulate classically with complexity theoretic evidence. So once we get these bit strings, a question is how to benchmark these bit strings, how to verify the statistics satisfy the probability of the desired probability distribution. So then Google came up with the linear cross-entropy benchmark to do this task. We use Xcb for short to denote linear cross-entropy benchmark. So Xcb is defined in the following way. Suppose we we multiply the two probability together for each bit string. The probability Pu is that defined by ideal circuit to getting the bit string x, and the Qx is the probability to get x by the noisy circuit or experiment. We multiply them together, sum over all the bit strings, and then with some normalization and the Bayes term. So we can also reformulate this definition in a more operational way. So we regard x, bit string x, as a random variable sampled from the probability distribution Q, and compute the expectation value of this function, a function of bit string x. So here we regard Pu, the ideal circuit probability, as a function from bit string x to real numbers. So the Xcb has several good properties. Firstly, that when P is roughly equal to Q, then Xcb will be similar to 1 for a chaotic quantum circuit. So which means Xcb is well normalized. And if P and Q are uncorrelated, then our Xcb will be 0. So this suggests that non-vanishing Xcb implies P and Q have non-trivial correlations. So this is a motivation to use Xcb to benchmark the experiment. So actually, Xcb is a linearization of more commonly used cross-entropy like KR divergence, which is widely used in data science, where we replace this px by log px and with different normalization and Bayes term. And we can also generalize it to other cross-entropy by other nonlinear function. So actually, there are several cross-entropy which satisfy these good properties. However, among these several candidates, linear cross-entropy has the smallest smallest statistical fluctuations when we estimate it empirically. So this is this is started in Google's paper by numerics.
So can I ask a question?
Oh, sure. Sure.
Good. So what do you mean by chaotic quantum circuits?
Oh, basically a random quantum circuit.
Okay, so it's really, I can just say random quantum circuit rather than chaotic, is that right?
And it can also come from Hamiltonian evolution, such that there is like quantum information scrambling. We also regard this type of system as chaotic, which means information is spread over the entire system. We cannot detect any useful information by local measurement.
Okay, thanks.
Okay, so actually, there are more motivations to use Xcb as a benchmark. So we found that there are basically two purposes of using Xcb in the literature. The first is to use Xcb as a proxy for fidelity. So in Google's paper, they show that the linear cross-entropy is similar, the value is similar to the many-body fidelity by numerics and some analytics but under strong assumptions. And also it can be used as a certification of quantum advantage because people believe high fidelity is hard to achieve classically. So its proxy, the Xcb, should also be hard. This is one motivation. Another motivation, another evidence is that actually there is a direct complexity theoretic evidence to show that achieving high Xcb is hard classically, but easy for quantum system. So after defining Xcb, I will briefly talk about how to measure it operationally. So suppose we have a noisy quantum circuit, or even just a classical classical computer which pretend as a quantum circuit, quantum device. So we measure the system, we get a bit string X according to the probability defined by this device. And then on the classical description of ideal quantum circuit is also given. So we can also compute the probability value Px for these bit strings by, for example, from a supercomputer. Then we can use this data to compute the empirical Xcb. So we can also compute the empirical Xcb by consider smaller size system, because this procedure is computationally hard. So we may consider small size system and then extrapolate the Xcb value for larger system size. So once we get the empirical Xcb, if it is large enough, we may claim there is a quantum advantage from this device. However, if it is very small, then there will be no quantum advantage due to, for example, the system is too noisy and or it is just a classical device. So it's more like a computational complexity version of Bayes inequality. So concretely in Google's experiment, they have a 53 qubits device, and the running time of their experiment is inside is smaller than 200 seconds. So they produce 7 million bit strings and achieving Xcb value larger than 0.002. And then Google claims that a classical computer, for a classical computer, in order to achieve this Xcb value with 7 million distinct bit strings, it will require 10,000 years. However, this claim seems to be challenged recently by several tensor network contraction algorithms. The very recent one, they also claim that they can achieve larger Xcb than this value with 7 million bit strings, distinct bit strings using just 5 days and with 60 GPUs, modest computational resources. So, however, people may argue there is some way to avoid their attack because the strings generated by these algorithms are highly correlated. So thus it's possible to distinguish the data from this classical algorithm from the data in experiment. But as far as I know, I don't know how to do this concretely because they can mix these correlated bit strings with uniform, just some random bit strings, and the average Xcb is still larger than this value. So okay, so is this result imply that Xcb is not enough to benchmark quantum advantage? So there is another way to avoid their attack. It's simply like extending the number of qubits from 53 to 70 qubits, which is also reasonable in near-term devices. So we may have some cost like more running time in quantum device, larger number of bit strings samples, and maybe a little bit less Xcb value. However, even though this classical algorithm will definitely fail due to their intrinsic exponential complexity in both space and time. So the key point is that these algorithms are not scalable, but the main motivation of quantum advantage is based on complexity theory. So we want to have polynomial in quantum device and exponential running time in classical device separation. So it seems that just simply scaling the system size, Xcb is also still a good benchmark. So is this the end of the story? So our result gives answer is no. we have different types of spoofing algorithm, and it seems that it can challenge the usage of Xcb as a benchmark for quantum advantage. So now let me give an overview of our results and introduce the new spoofing algorithm. So in this part, first I will give I will describe the quantum circuit model we consider, which is a quantum random circuit, unitary circuit, and then I will give a description of our spoofing algorithm. Then I will present the key results of our algorithm, including the scalability of the algorithm, and I will also discuss Xcb versus fidelity from our algorithm. Then I will talk about the implication on the two usage of Xcb. So first, random unitary circuit. So random unitary circuit is a quantum circuit composed of many 2-qubit random gates. And those 2-qubit random gates is chosen from some gate ensemble. I will talk about it right now, just later. So, and then we have arrangement of qubits on either a one-dimension 1D chain or 2D plane, or a 2D lattice, or some other lattice like Google's Sigma architecture. And then for each layer, we have a bunch of 2-qubit gates, and then we apply it many times. We apply D layers of 2-qubit gates, and this D is called depth. So for each 2-qubit gate, the gate ensemble we considered in this talk is the following. So we have some 2-qubit entangling gate, and around this entangling gate, we have 4 single-qubit hard random gate. And these hard random gate are chosen independently. And the meaning of hard random means if we apply this gate to some fixed initial state, we will get some state which are uniformly distributed on the Bloch's field. So the 2-qubit gate can be either some fixed gate, or it can be chosen from an ensemble. So in this talk, we only consider 3 such kind of 2-qubit gates. One is the control Z gate. Another is 2-qubit hard random gate, which is a 2-qubit generalization of this one qubit version. So, and we also consider F-same gate, which is the gate used in Google. So which is basically a time evolution of Heisenberg interaction up to some phases. So then the question is, once the random unitary circuit is given, is the Xcb really hard to spoof by the classical algorithm compared to a noisy circuit? So let's consider a simple example of a spoofing algorithm. So first, we want to come up with a classical algorithm which should be compared with a noisy circuit. The noisy circuit can be from like experiment, and in noisy circuit, the noises truncate the entanglement or correlations effectively among subsystems, and this motivates us to come up with a classical algorithm. Instead of using uniform distributed noise, we may introduce some noise in a different way. So the noise we consider is simply gate defects by just omitting some gates, such that we remove the correlations among subsystems explicitly. Then the system will decompose into isolated subsystems. So because each subsystem is uncorrelated with each other, and its size is much smaller, so it's much easier to simulate classically. So one thing I want to emphasize is that our algorithm is not used to simulate the noisy circuit, but we have an algorithm, we can get Xcb, and for noisy circuit, it also has Xcb. We want to have algorithm, the Xcb, to compete with the Xcb from noisy circuit. Okay, then the result, the performance of our result. First, we consider a simple situation, which is a 1D hard random circuit, which is widely studied in some theory papers of quantum advantage. So, so for this ensemble, we have a linear time classical algorithm, which outperforms any noisy circuit for large enough number of qubits in Xcb test. And the strength of noise can be arbitrarily small as long as it does not scale with the system size. It should be a constant. So more concretely, in our algorithm, we can get the mean value of the Xcb over different circuit will exponential decay with depth, and the decay rate is denoted as that1. And the standard deviation or the fluctuation of Xcb of our algorithm over different unitary also exponential decay with depth. And then we numerically show that for a large enough subsystem size, the decay rate between STD and the mean value is similar, which means the result for mean value represents the typical case of a different unitary circuit U. And we also consider Xcb for noisy circuit, and we found that it also exponential decay with depth, and even when the strength of noise tends to be 0, but because we are considering large number of qubit case, so we also require n times epsilon is greater than 1. So in this vanishing strength of noise limit, we can define a decay rate -3, and we found that the decay rate of the noisy circuit is larger than our algorithm. And we found that after a subsystem size larger than 15, it will approach it to a constant. So we only need to simulate a quantum circuit. The subsystem has constant size. So this is the linear time classical algorithm. And for Google's architecture, the Sigma architecture with 53 qubits and 20 depths, we have our algorithm is super fast. The running time is smaller than 10 seconds using only 1 GPU. So in this case, we found that our algorithm had Xcb comparable to Google's value in several settings. The first is that in our algorithm, the Xcb can achieve 0.007 for hard random gate, and the Xcb can achieve 0.024 for control Z gate. So the partition of our system to subsystem is shown in the following way. This is a layout of Sigma chip, and then we simply skip the gates represented by red lines. And for F-sim gate, which is used in Google's experiment, so we direct applying our algorithm, the Xcb value we get is much smaller than Google's value. However, we can amplify the Xcb by a heuristic post-processing with what we call as power k method, which means we simply reweight each probability for each bit strings to the power k, and then a normalization. And by supported by analytics for toy model and numerics for Sigma circuit, we found that the mean value of the Xcb can be amplified by k times. And we found this relation holds up to k roughly equal to 10. Yeah. And then we also consider the scaling to more qubits by extending to more qubits. And we found that in noisy circuit, the Xcb usually decreases, but for our algorithm, the Xcb usually increase. So this is a result for a 1D circuit. And we also consider 2D circuit. So in this case, we increase the linear size. And when we increase the linear size, the number of gates skipped is also increasing. But in this case, the Xcb also increased in our algorithm. And we also consider extending Sigma chip to 71 qubits in this way. And then we found that the original algorithm can achieve 10% of Google's expected Xcb value. But when we apply the power K method, we will find at the number of qubit 51, it will outperform than Google's value. So this result shows that our algorithm has better scaling for achieving high Xcb, and by increasing the number of qubits, it will eventually outperform noisy circuit. Okay, so in summary, we have in 1D hard random ensembles, we have linear time classical algorithm, which is better than any noisy circuit. And for the 53 qubit sigma architecture, we have a super fast classical algorithm achieving a comparable Xcb value to Google's. And then our classical algorithm has better scaling with system size than noisy circuit. So this result challenge Xcb as a scalable measure to directly certify quantum advantage. So although there are some gaps to fully spoof Xcb, for example, so we only extend the sigma chip in this specific way, and the power K method, we can only guarantee the expectation value, and we don't know how to analyze the fluctuation over different unitaries. So there are still some gap. But what I want to what we want to show is that our algorithm is just an example, and it is pretty simple. So there is a lot of room to improve. Then then we consider Xcb versus fidelity in our algorithm. So here is the numerical result. And we found that for our algorithm, we produce a product state, and then the Xcb value over the fidelity is very, very huge. So which means in our algorithm, Xcb highly overestimates fidelity. But for noisy circuit here, we consider independent and identical single qubit noises. And we found that if the noise is large, then there is more estimation, overestimation for using Xcb to estimate fidelity. And we also observe that if we fix the strength of noise, the overestimation is minimized by fsim gate. So fsim gate is basically the one used in Google's experiment. So the first two results shows that Xcb could highly overestimate fidelity. So it's not a good proxy for fidelity in general case. However, the last result, which basically we started in detail assuming independent weak noise. We found that fsim is optimal for estimating fidelity by Xcb. So we can see in this numerical data. So if the strength of noise is small, for all the gate set, Xcb is similar to fidelity. But if we increase the strength of noise, we found that for contra Z gate, Xcb can highly overestimate fidelity. But for fsim gate, Xcb is still similar to fidelity. So this is shows that the choice of Google using fsim is very good. So in summary, we found that Xcb as a proxy for fidelity is not conditioned. So the conditions, if we want to use Xcb to estimate fidelity, these conditions should be checked experimentally. So violation of these conditions are like the loopholes in Bayes test. So then some discussions. Since we found that directly using Xcb is not a good scalable certification. However, we found that under certain conditions, Xcb can estimate fidelity very well if we use fsim gate. So maybe this inspires us to come up with other measures for a quantum advantage. Actually, the original quantum supremacy protocols are based on the so-called total variation distance. which is basically the R1 norm between the ideal, the target probability distribution and the distribution from experiment. So this is used in like boson sampling, Ising dynamics, and even theory for random unitary circuit. However, this measure is hard to estimate experimentally. So, but we know that if we have high fidelity, then this will imply this quantity is also not small. So this may inspire us to use Xcb indirectly to certify quantum advantage. For example, Xcb can be used to estimate the fidelity only for the noisy circuit or the experiment. But in this case, we need to make sure that the weak independent noise condition is satisfied. But the Xcb itself is not used as the score for a classical challenger to achieve. The score could be like the total variation distance. So the Xcb is only used to support that experiment achieves high fidelity that have other high score for other benchmark. So, but however, these types of argument is based on Xcb should be a good proxy for fidelity. Okay, in conclusion, we show that Xcb is not a good measure for both estimating fidelity and certifying quantum advantage without further assumptions on experiment. So checking loopholes or new benchmark is required. Okay, so any questions so far?
Okay, I do. So I have two quick questions. So first, did Google already know that Xcb is not a good proxy to fidelity, or they don't discuss this in their paper?
I didn't find discussion on this point.
So they didn't really discuss how good Xcb as some estimate of fidelity in their paper. So they just didn't address this question.
Yeah.
So, okay, so my second question is, so you have this, algorithm basically, take the circuit and divide it into two subsystems, then they calculate this Xcb. And either limit asymptotically seems like yours and diverge from theirs. So I think you said theirs will decrease, yours will increase.
Yeah.
So it seems like then those two things, what Google did and what you calculated, there are two different Xcb. Is that right? They are. So it seems like your algorithm is not directly related to their Xcb. It's just a way to show that, some Xcb is very different from fidelity. Or that's the right interpretation of your algorithm?
Yeah, so this is basically related to the second usage. There is some complexity theoretical support to show that achieving high Xcb is hard by classical computer, but easy for quantum device. No matter, this is regardless of whether Xcb approximate fidelity. So we will only care about the value of Xcb. And they claim that in order to achieve high Xcb, it's impossible classically. But we show that at least if they increase the number of qubits further, it is not the case as they expect.
I see. So, but to me, it seems more reasonable as you asymptotic more qubit Xcb should go down. But I think you disprove this complexity thinking that it's hard to do classical. Actually, you can do it by your calculation, right?
Yeah.
Okay, so I assume you will address this later. So there's this delta 1, delta 2. I assume they have a physical interpretation. You just said they roughly equal. I assume you will discuss more how equal they are, right?
Oh yeah, so actually there is still a gap, but our simulation ability can only simulate the same size for TD up to 15 qubits.
I see. I would, really like to know roughly how you can get, their convergence or something. Anyway, I think that probably will come up from your discussion later. Thanks.
Yeah. So actually, for noises, the mean value, if we only consider mean value, delta 3 and delta 1 has a good interpretation using Ising models. They are related to symmetry, how the amount of violation of Z2 symmetry, and these are also related to like spontaneous magnetization. When we decrease the strength of noise, it's still an open gap. Yeah, I will talk about it later.
Okay, thanks.
So I have a different question. Do your results have any implication for the Ustc experiment?
No, they use different benchmark. We haven't looked at the detail. But I want to say that they use different benchmark, but their benchmark is not it does not have a strong foundation as Xcb. Because Xcb, we show that we found that Google discussed that it's similar to fidelity. So this is the first evidence to use Xcb, although we disprove it. And the second is that there is a complexity theoretical foundation to support using Xcb. But in Ustc's experiment, their benchmark is not well started, so people don't know how strong evidence this benchmark has.
Thank you.
Yeah. Okay, so in summary, we show that our classical algorithm has better scaling with system size than noisy circuit in terms of Xcb. And we also show that Xcb can overestimate fidelity in general case, but sometimes the overestimation is small. So we will show that this could be understood by a mapping to by a statistical physics model. So then let's discuss this mapping. So the high-level idea is the following. Actually, recently there are many works on mapping random unitary circuits to statistical physics model. For example, the RUC can be mapped to Ising spin model and also quantum spin chain. These two mapping are extensively studied in the recent literatures. And in this talk, I will discuss another mapping to diffusion-reaction model, which is convenient to study Xcb versus fidelity. And the key point is that analyzing an individual quantum circuit or dynamics is extremely difficult. However, if we consider ensemble of unitaries and then after taking average, the average behavior is much easier to analyze. So then in the rest of this talk, I will introduce how does this work. First, I will give a high-level picture of how the classical degree of freedom, like how does spin degree of freedom in Ising model emerge from random unitary circuit. And then I will discuss give the mapping from Xcb and fidelity to a diffusion-reaction model. Then we use this model to explain when Xcb is similar to fidelity and to understand the scaling feature of our algorithm. So first, how does the classical degree of freedom emerge? Let's consider a simple example first. Suppose we only have one copy of quantum state represented by the density matrix, and we apply operation U to it. So we have U and U dagger for density matrix. After taking average, if the unitary is random enough, for example, chosen from hard random ensemble, we will get trace row and then maximally mixed state. So this diagram represents trace row, and this represents the identity. And actually, we can also regard this as a vector, but with two qubits. So this is basically the Troy representation, the channel state duality. basically we flip this the dual vector to vector. So then in this case, if we only focus on the operation itself, we will have this equation. This can be understood as a projector of EPR pair. So then the physical picture of this result is that after taking average, all the information is deleted except the normalization condition, which means a trace row is only trace row is preserved. All the other information is deleted. Then let's consider two copies, which is related to unitary two design property. In this case, we have two copies. One copy might be from ideal circuit, another might be from a noisy circuit. So this is the two copy. Then after taking average over this operation, we will get we can use the Weingarten formula and written it in a diagram in this diagram. So it consists of two terms. This term can be interpreted as a projection on the symmetric part between these two copies. This term represents the anti-symmetric part between these two copies. So why this is anti-symmetric and symmetric? So this diagram can be is basically the trace row 1 times row 2, because diagrammatically, given the input row 1, row 2, we will get just this diagram. And this diagram represents the trace row 1, row 2 with swap operator. So because if we just reshape it, we will find this is simply swap operator, trace with swap operator. So the picture is that in this case, with two copies, all the information is deleted except the normalization condition and the symmetry with respect to the symmetry of a swap operator, which could be either symmetric or anti-symmetric. So pictorially, we can represent the result by this diagram. So these 4 lines represent the 4 qubit lines. And however, we only have actually effectively 2 degrees of freedom. We use dotted line to represent them, which could be either labeled by either symmetry or anti-symmetry. So this circle can be understood as a species, index species converter from the effective degree of freedom to projector on the 4 qubit lines. So besides the degree of freedom symmetric and anti-symmetric projector, we can also consider other effective degree of freedom by taking linear combination between these two. For example, we can also get identity and swap, which represent Ising's spin model. And then another is some other type of linear combination, which denoted by omega and identity. We will talk about this in detail later. This case, this will correspond to diffusion-reaction model. So then we use this above idea to get the mapping to diffusion-reaction model. So let's consider linear cross Xcb for the ideal circuit first. So we have 2 copies of probability, and so then this so we basically have 4 copies of single-hard random unitary. After taking average value, we will get this this structure. So in this case, here the dotted line is labeled by identity and swap degree of freedom. Oh, sorry, identity and omega degree of freedom. And later we will view identity as a vacuum state and omega as a particle occupied at this position. So for 2 qubit gates, we use this to denote it. Then combining these ingredients together, we will get this diagram. And notice that each dotted line should be summed over identity and omega state. So this should be this should be summed for all the space and time positions. So this is basically a diagram for this value. And then after direct calculations, we show that this structure, which has only one dotted index, which should be a vector, and we show that this represent a uniform distribution. And this is identity operator and this is a dual vector, and this is it's a gate state dependent, and we found that it is a 4x4 Markovian transform matrix, which represent probability transition from 2 bits to another 2 bits, and each bit is represented by a dotted line. And then we can interpret the above the diagram as a diffusion-reaction process, the horizontal direction as the time direction. The first column represents an initial state, which is a uniform distribution. And then we have a successive applications of Markovian evolution. And up to the last layer, we will get a probability distribution denoted as a vector P. And then we want to compute the inner product with the dual vector for the right boundary condition. So we basically want to compute this. And this is can be interpreted as a path integral of a weighted sum for the last layer. So which means if we have on the last layer, if we have identity state, we will get a weight 2. If we have a particle omega, then we will have a 1/3 decay, two-third decays, two-third weights. So the relative weights 1/3 in this weighted sum can be interpreted intuitively, because Xcb is only measured in Z basis, but the omega actually represents 3 species X, Y, and Z. So among these 3 polys, only the information in Z can be detected. That's why we have a 1/3 weight. And the factor 2 is basically a matter of normalization. We will see it later in detail. So look into more detail about the transform matrix. The transform matrix can be interpreted as a diffusion reaction process. So each entry can be interpreted as a probability transition from this state to this state. And we can also compute the transform matrix from control Z and Fsim gate. So then on the diffusion, there are 2 processes. One is diffusion process. We have particles and with some probability change its position. So this is basically a random walk process. And we can also show that if the gate has more entanglement productivity, then we will have larger diffusion rate. And so the speed of random walk, we have this order. Fsim is the fastest. We have also another process, reaction process, which includes particle duplication and recombination, such that the number of particles is not conserved. So we can define the diffusion rate, which is a ratio between the duplication probability and over the recombination probability. We can show that it is always 3, which is gate state independent. So why this is 3? Because intuitively, omega represents 3 species, X, Y, and Z. So we have talked about how to map Xcb to diffusion reaction model. Then let's consider fidelity. So fidelity is defined as trace row 1, row 2, if one of them is a pure state. So this is basically row 1 times row 2, and this loop represents the trace of row 1 times row 2. And then we can reshape this diagram. We can get this diagram, and then this is basically the boundary condition for the last layer. Then according to some calculations, we found that this represents a dual vector 1, 1. So in summary, the Xcb is a weighted sum of particle population in the last layer, but fidelity is just the unit product between these 2 states, which is simply a normalization, probability normalization, which is of cross 1. So it's represent total sum of particle population. So the main message is that in both Xcb and fidelity, everything is the same in the mapping, except the boundary condition on the last layer. So now let's apply the above model to explain when Xcb is roughly equal to fidelity. So because they only differ on the last layer, so we need to consider the distribution on the last layer. So let's consider a limit case first, the stationary distribution of that last layer when there is no noise and the long-term limit, which means the circuit depth, circuit is deep. So we can show that the particle population will equilibrate to this stationary distribution, such that for each position, each position is independent with each other, and we also have a 1 versus 3 weight for omega and identity and omega. So this result is entangling gate independent, which is fully determined by reaction rate. So intuitively, why we have a 1 versus 3 weights? Because in a chaotic system, the final state should have a uniform mixture of identity X, Y, and Z. But the identity labeled by vacuum only has one species, but omega has actually corresponds to XYZ, which has 3 species. So that's why we have this 1 versus 3 weight. Actually, in fact, this distribution is not precise. The true distribution should be this distribution up to some small correction. This small correction is used to eliminate the -1 in the definition of Xcb. So I just skip the detail here. So we can illustrate the final distribution as this diagram. The y-axis represents the density of omega state at the last layer. So we found we show that this should be a homogeneous distribution, and this is a possible configuration for the last layer. So then this distribution is fully determined by reaction rate. So how does diffusion rate also plays a role? The answer is yes, because the time to reach the equilibration depends on the diffusion rate. Larger diffusion rate, the mixing time is short. And so the mixing time can also be understood as a scrambling time in a chaotic quantum system. So then let's compute Xcb and fidelity. So Xcb is a weighted sum. We have weight 2 on identity and 2/3 on omega. And we compute this on inner product. We will get 1 for each position. So that's why we have Xcb is roughly equal to 1. And then for fidelity, it's simply a normalization of probability. So we have equal weight on identity and omega. So it's across 1. So this explains why fidelity approaches to 1 in chaotic system without noise. Then let's consider the effect of noise. So in this case, 1 copy of the probability should be replaced by Qx for noisy circuit. And the difference is only that in somewhere we insert a channel of noise, and then we only have 1 copy of noise. And so then we use this notation to denote it. And then after converting the species from 4 qubit lines to identity and omega degree of freedom, we will get a diagonal matrix. And when we have omega, we will see we have 1 minus epsilon decay. We can view this as a particle loss. So we can illustrate the result in the following diagram. This is a summation over all the weights of the histories of particle diffusion reaction process. This is one possible history of particle evolution. And then after considering noise, we will have 1 minus epsilon decay to the power of the total number of particles during the history. So this leads to particle loss. The particle loss leads to the decline of Xcb and fidelity. So then let's consider small noise case, which is basically the perturbation from the ideal case. So a weak noise means the equilibration time is much shorter than lost time. So in this case, the final states and the history approximately decouple. So both identity and omega experienced the same amount of loss alpha. So which means the probability distribution only rescaled by a factor of alpha. So because it's just a rescaling, so the distribution will give the same Xcb and fidelity, which is roughly like alpha to the power n. And we have some numerical data to show that if the strength of noise is small, all the Xcbs are similar to fidelity. So if we consider non-participative regime, we have reshaped the probability by factor alpha for identity and beta for omega. So we can show that we can show that alpha is larger than beta, which means identity suffer less decay from omega. This is intuitively, this can be explained intuitively because the final state and the history in this time are correlated. So if we observe identity in the last layer, so it's more likely we have identity in the previous layers. So which means it suffers less from particle loss. That's why we have alpha larger than beta. So in some,
快完了，还有2分钟。
So in summary, we have in Xcb, the state identity which suffer less from noise has more weights. So that's why Xcb is larger than fidelity. Oh, sorry. Then here is a numerical simulation to show that when noise is large, like only 2%, we will say there is a large discrepancy between fidelity and Xcb for like control Z gate. But the discrepancy is minimized by FSIM gate. This because FSIM gate produces more entanglement, so the diffusion rate is large. So there is a faster equilibration time. Then finally, let's apply the model to understand the scaling feature of our algorithm. So we observe that in the above discussion, we observe that if there is a deviation from the distribution, then there is a discrepancy between Xcb and fidelity. So this provides another motivation to come up with our algorithm to spoof Xcb. We can simply disturbing this distribution dramatically. Then the skipped gates corresponds to only one copy of unitary U and U dagger. So this is unitary 1 design. All the information is deleted. So there is a strong this corresponds to strong depolarizing noise, and this will violate the homogeneity of the distribution. So here is an illustration of the effect of our algorithm. The dashed line represents the skipped gate, and if the particle does not hit the skipped gate, the weight is still contribute to Xcb in our algorithm. If the particle hit the region of skipped gate, and it will be reset to 0 since the strong noise limit, it corresponds to a projector. So then let's consider why in our algorithm Xcb highly overestimate fidelity. So the skipped gate position can be imagined as a sink. Around this sink, all the particle omic will disappear, so only identity remain. And this works for both Xcb and fidelity. The only difference is the weight are different. So we have weight 2 for identity in Xcb, but weight 1 for identity in fidelity. So in summary, Xcb has a larger weight for identity, and there are a lot of identity in our algorithm. So that's why Xcb highly overestimates fidelity. And then we can also consider increasing the system size. Then our algorithm has better performance because in this case, there are more rooms for particles to escape from the loss. And different effects for different gate set. We found that the Xcb for FSIM gate is much smaller than control Z because the diffusion rate of FSIM is much larger. So it's easier to hit the loss region, which leads to much less Xcb. Okay, so then conclusion. So in this talk, we show that Xcb is not a good measure for both estimating fidelity and certifying quantum advantage if without further assumptions on the experiment. And we also introduce a mapping to statistical physics model, which is an interesting approach to understand random unitary circuit. For example, the explanation when Xcb is similar to fidelity. Yeah, that's all. Thank you for your attention.
Well, thank you very much for a beautiful talk. And I'm sure there's going to be a great deal of discussion. So I'd like to have people turn on their video when they talk so we can actually have a face-to-face meeting.
Okay, so if nobody else asks, I will ask again. So there's something I didn't quite understand, which is I think you said a certain point when you have the map from random unitary circuits to this diffusion model, there's some kind of universality which is independent of the entanglement gates.
Yes.
But in the end, you also said the cross entropy seems to depend on what you choose for the entanglement gate. You know, control Z is bigger than harm and bigger than the Google one.
Yeah.
So what's the difference in these two things? Because I assume you just map the Xcb to diffusion model, then everything is extracted from the diffusion model. If that's universal, then how could you see the difference between the entanglement gate?
Oh, the reaction rate is fixed, which determines the number of particles, but the diffusion rate is gate dependent. For FSIM gate, the diffusion rate is larger than control Z gate.
Oh, I see. So when you say universal, so there is some quantitative difference, which is the model has parameters,
Yeah.
and it depends on, you know, which entanglement gate you are choosing. Then that's the numbers are different when you get the Xcb out of this.
Yeah. So basically, we show that for ideal circuit and a deep enough circuit, the stationary distribution is a universal property, which is gate set independent. However, when we consider finite types and also, for example, we introduce noise, then in this case, the reaction process is not enough to determine the behavior of the system. And then in this case, diffusion process will dominate. But for diffusion process, it is gate set dependent.
I see. So just quickly also, it is also true that the map from this random unitary circuits to a diffusion model is independent of the 1 qubit sample too. So I think you defined a hard measure uniform for 1 qubit gates using a reference state. You choose, you know, the one state, and then you define uniform by, you know, asking all the gates acting on this particular state become uniform on the block sphere. So is that obvious that this is independent of the reference state? You know, it's a uniform, doesn't matter which state you start with?
Yeah. Once we fix it, it is independent of the initial state.
Once you fix
the reference state, then the resulting state has the same distribution uniformly on block sphere.
No, I'm asking if does this depends on the reference state? Well, the thing is, different state really by some unitary, but the unitary might complicate it according to your gate set. So
So it only works for single. That picture only works for 1 qubit example. But when we consider a quantum circuit, it will be depending on many different different aspects.
So one last thing is I don't really see, you know, further discussion about this delta 1, delta 2. You know, in the Ising model, you have temperature,
yeah.
you have an energy gap. They have an interpretation using the energy gap, the temperature, all those quantities?
Yes, it's related. And because the time limit, so I skipped it. Maybe I can discuss it.
Right.
So
Yeah.
actually, we can apply a similar idea by using the emergent degree of freedom concept, but using different bases. So in this case, each 4 copies of the entangling gate will correspond to 2 Ising spin model. So maybe this diagram is not good. Sorry. Or maybe this one is better. So after taking the average, 1 gate will correspond to 2 spins and with 1 type of interaction. And then the hard part will correspond to another type of interaction. Then we can combine them together. And then it is mapped to an Ising spin model. And this Ising spin model has a Z2 symmetry. This Z2 Ising symmetry reflects the fact that because we consider V tensor V star tensor V tensor V star, so we have a permutation symmetry, like to permute this 2V or this 2V star. So this symmetry will correspond to the global Ising symmetry. So then we have a mapping such that the partition function of this Ising model equals to Xcb plus 1. So for ideal circuit, we also have Z2 Ising symmetry. Then by some transformation of the model, we can also find that there is only long domain wall can exist. So which means this should be in the ferromagnetic phase. We have a 2 stable ground state, two degenerate stable ground state. And then we can discuss on ideal circuit, our algorithm, and the noisy circuit. So, we can consider the we can define the transfer matrix T, and then the Xcb is roughly speaking is a trace T to the power of D times D is the depth. And then in ideal circuit, we have Z2 Ising symmetry. So which means the second largest eigenvalue is still 1, the gap is 0. So which means Xcb plus 1 is 2. So Xcb approaches to 1. But for our algorithm, the skipping gate will be replaced by a very strong magnetic field on the boundary. So this will violate the Ising symmetry, which will open the gap. And for noisy circuit, we have a very weak strength of field, magnetic field over the bulk. Then this also violates Z2 Ising symmetry. Then we basically we want to compare the amount of violations between our algorithm and noisy circuit. So basically, the 2 scenarios of Ising magnetic field. And this then we numerically calculated this. And for our algorithm, we simply calculated it, and we draw the scaling with the subsystem size. But for noisy circuit, we do the extrapolation. We consider large n limit and start from finite epsilon, and then we make the epsilon smaller and smaller. Then we can get the limiting value when epsilon is 0. Then we can define the gap for the noisy circuit. And when we make the epsilon equals to 0 limit, we still have a gap. This is related to the spontaneous magnetization because it's in ferromagnetic phase.
What does the corresponding phase transition tell you about this model?
Oh, sorry, no phase transition occurs here.
No, but there will be a phase transition in the Ising system. So at that point, there should be some reflection in your model.
Oh, so in our model, the temperature and the strength of interaction is fully determined by the local degree of freedom for one. Basically, it depends. It is determined by D in QD. If D is fixed, here D is always 2 in our consideration. So the interaction and temperature is fixed.
Mhm.
And it is belongs to a stable phase, which is a ferromagnetic phase.
Okay, thanks. But I just have one comment, which I think I find this really kind of exciting direction, which is somehow, in a sense, what you did is something like, we kind of know, which is a quantum circuit is nothing but a time-dependent Hamiltonian. So when you take up ensemble, somehow you figure out that for this particular ensemble, you get a SPT, which is the Ising. So I wonder, I don't know how hard it is. You could find another ensemble, get another SPT in Z2, which is the double semia. So apparently, somehow the ensemble encoded that when you map to this model is a gapped ferromatic, Ising model, which is a Z2 SPT.
Mm-hmm.
So that information has to come from the entangling gate or something, right? That's the only thing which will determine it.
Actually, in this in this let me see the last paper actually basically extend this idea. They consider different ensembles, but also introduce a weak measurement to tune the strength of interaction. Then they find many different SPT phase, which basically map to quantum spin chain with different SPT phases.
Oh, I see. But that seems to be a different parameter I'm thinking. So you said they just tune the strength.
Oh, not strength, also the type of ensemble.
Okay, because I'm thinking, this is basically something, random circuit model is nothing but time-dependent Hamiltonian. So all you need is to turn into an ensemble of Hamiltonian. And then random matrix theory will come in, pick out the symmetry. And that's what comes from the circuits.
Yeah.
Okay, thanks.
So are there any other comments? Anybody else have a question? Well, I would really like to thank you again, Xun. You gave an absolutely beautiful talk.
Thank you.
It's just the start. Now I can see of a very long discussion, and it's really very important to understand the different ways to look at quantum supremacy. And I look forward to hearing much more about it in the future. So thank you again, and
Thank you.
see you next week.
That actually is a great talk.
Thank you.
Bye-bye. Bye-bye.
Bye.